Okay, I guess we can get started. So today we are going to talk about instrumental analysis. So we have 6 items to talk about today. So I will give a brief introduction about the instrumental analytical methods, and then I will be focused on by conducting analysis by light and by color. And then I will talk more about how to prepare samples to satisfy the QA and QC requirements. And because this part is a little bit abstract, so we are going to go through some of the examples. And this example will be also shown in the homework assignment. So first, let's look at the analytical methods. And so there are some common analytical methods, like we have the optical method, like this one, and we have the electrical method, like the pH meter. And we also like the chromatography, like something like this. I will talk this more later. And we also have some other methods, like to conduct a measurement by mass. And so first, let's look at the optical method, because we are also going to use the similar instruments in our lab. Optical method is also called spectrophotometry. This is a method of analysis. I guess I'm recording. Oh yes, I'm recording. Conduct analysis that involve how light interacts with the atoms or molecule in a sample of matter. So this is a useful and often used method to determine the concentration of a chemical in a solution, especially if the solution has a color. And it can also make the measurement. It measures the intensity of the color and relates the intensity of the color to the concentration of the solution. So basically, we can construct the functional relation between intensity of color and the concentration, and then we can use the new intensity to estimate the concentration of the solution. I will show the example later. And here I want to emphasize that when we are speaking of light, it refers to all of this here. So in general, we may have some visible light, but visible light is only a small part of the light. So for the spectrophotometry, we may also use some light instead of the visible light. And here are some examples. There are some related instruments that is based on spectrophotometry. And the first one, let's say this is UVV's spectrophotometer. And we can see the UV here refers to ultraviolet, and the V refers to the visible light. So basically, this instrument can use ultraviolet light and visible light. And we have some other examples like this one. Actually, I haven't used this instrument before, but we can see this also used like infrared light. So basically, we can use some other types of light. And in this class, I think we are going to use ICP in the heavy metal lab, and we are also going to use GC, which is not here. Okay, so we are going to use these instruments in the heavy metal lab. And here are some other examples. And then let's talk about some relations between intensity of color and the concentration. And this is based on Beer's law. So this is an empirical relation that relates the absorption of light to the property of the materials through which the light is traveling. And here is the expression. So this is obeyed over a limited concentration range and can be represented by this equation. So in this equation, A refers to the sample absorbance. This is a measure of intensity of the color produced. And this is a unitless value. And here C refers to the molar concentration. So this is the concentration of the chemical in our solution. And the rest of them, eta refers to the molar absorption coefficient. And we can see that for a given chemical, this is a constant. So this is a fixed value. And AO here refers to the optical path length. So basically, when we have a solution and we have the input light, this refers to the length of our solution. And we can also see that for a given instrumental configuration, the L is also a fixed value. So this is also a constant. So basically, we can have the linear relation between absorbance and the concentration. And on the right side, here shows the like an example. We have the concentration here, and this is the absorbance. And we can see they have a linear relation. But we need also be careful that this should be only for a limited concentration range. In other words, if the concentration become very large, then it will be something like this. And if the concentration become very low, it will be something like this. That's why we need to pay attention to the limited range. And that's why we also need to make the calibration curve. And this picture shows the relation between wavelengths and absorbance. And here are the curves of different concentration. We can see that as the concentration increase, the absorbance also increase, which reflected by this picture. But we can also see that by using different lights with different wavelengths, the absorbance will also change. Like for this chemical, when we use the light that has about this wavelengths, then it can absorb more than other wavelengths. By the way, for light at this range, I think this is about red color, or green or red. Oh, so for this one, do you guys have any questions? Yes.
Does the curves tend to be like the curve for like one specific chemical? Yeah. Does it usually peak at the same wavelength the whole way?
For a given chemical,
yeah,
it is at the same peak.
So it tends to do that all the time for. So like if it was a different chemical, all the peaks would be at like let's say 500. Like all.
Yeah,
okay.
For different chemicals, the wavelengths may be different.
Okay.
And the curve shape may be different.
Okay.
Yeah, like as far as I know, for some chemical, it may have 2 peaks.
Oh.
Yes. So any more questions? And here is like for several years ago, like for 11, we have some experiments like this. So we have some outflows, and then we collect the concentration of the outflow. We can see the concentration gradually increase. And then we use UVVs to measure the concentration. But because this experiment is a little bit unsafe, so we just remove this experiment. Okay, so let's look at the chromatography, which is based on color. So chromatography is a method of separating components of a mixture based on their relative affinity for partitioning between different phases. And so basically, we know that every molecule or element in a mixture, they have different properties. And because they have different properties, they can travel at different speeds as they partition between mobile phase or stationary phase. And this is a little bit abstract. Let's look at an example. So suppose we have a solution and we have a paper here. So this is a paper and we have the black ink. We know that black ink is a mixture of the ink of different colors. And here we have water. And we know that because of the capillary effect, when we have this paper into the water will go up. And as the water go up, the water will carry or take some of the ink also go up. But because different ink, they have different speed or they have different affinity to the paper. So different ink will travel at different speed. And finally, we will have something like this. And in this case, we can see the yellow dye travel very fast, and the red dye travel relatively slow. And in this way, we can separate the ink of different colors. I guess because the very original theory is based on like these colors. That's why it is called chromatography. So for this one, do you guys have any questions? Oh, and in this case, the mobile phase refers to the water, and the stationary phase refers to this paper. And the ink is our sample. And because this method, we can separate different ink, and we can imagine if we have this paper long enough, and finally these dyes will be separated. And this can be applied in chemical analysis because we can separate different components. So this method can be used for purification and can also be used to measure proportions in a mixture. And nowadays we have different configurations based on the same theory. So suppose we have the burette, and in the burette, we can fill some of the sand. Like in this case, like we may have some sand here as the stationary phase. And we also can have our sample here. And our sample may contain different chemicals like DDT or DDE. And then in this case, we can also add a mobile phase. For example, like water or DI water. And then we use this DI water to flush our sample. And then we know that the DI water will just go down. And because different chemicals has different affinity to the sand, so they will travel at different speed. So for example, this one, this blue or green one, it travels fast. So if at first, when this green one goes down, we can collect it first. And then when this yellow or orange one goes down, we can collect it next. And finally, we can separate the components of this sample. And in terms of this process, we have like different terms to describe. And the first one is effluent. So this refers to the solvents or solvent mixture used in illusion chromatography, and this is similar to the mobile phase. So effluent just refers to the stuff that's coming out from this burette. And for the immobile phase, it is also called a stationary phase. So that is immobilized on the support of the particle or the inner wall of the column of tubing. And in this experiment, the sand here refers to the immobile phase or stationary phase. And the mobile phase, on the other hand, refers to the phase that moves in a definite direction. And in this case, the mobile phase refers to the DI water. We also have a term that is retention time. This is a characteristic time it takes for particular analytes to pass through the system and from the column inlet to the detector or to the outlet, like under set conditions. And in this case, we have two retention times. One is retention time of this orange chemical, and another retention time is for this green chemical. So different chemical or each component, they will have their own retention time. And we also have a detector that is the instrument used for quantify the amount of analytes. And in this case, the detector is not shown, but when we are measuring the concentration of the chemicals in each effluent, that is a detector. And we'll also have the analyte, that is a substance to be separated during chromatography. And so for this one about this concept, do you guys have any questions? No? Okay. But for more nowadays or for modern instruments, we can have something like the gas chromatography or liquid chromatography. So in general, we have the similar theory, but we change our tubes. And this is the inside of a GC column. So this is a gas chromatography. And this is the column, or this is a tube. And the tube is something like this. We can see this tube is very long and very thin. In this case, as far as I know, this is about like 30 meters in the column, in the GC. And in this case, the stationary phase is the inner surface of this tube. So we didn't add anything into this tube, but we just use the inner surface of the tube as the stationary phase. And we also have some other columns. And this is the GCMS. And we also have HPLC, and which is a liquid phase chromatography. And this is a column of HPLC. We can see this is a little bit shorter. And as far as I know, we feel like we have some stuff inside this column as the stationary phase. And I think in tomorrow's experiments, or for the experiments in the next week, we are going to use GC to measure the organic pollutants in our soil sample. So far, do you guys have any questions? Or if you have questions, you can just type in a comment in the chat. Now, by knowing the instrument, we are going to prepare samples. We prepare samples because we want to measure the concentration of the pollutants in our sample. But another purpose is to make sure the QA and QC is satisfied. So let's recall that QA refers to quality assurance. It refers to the overall strategies for obtaining a quality product. And QC refers to quality control. It is the tactics which are used to measure and control the quality. So basically in practice, when we are talking about QA or QC, like if someone asks you what's your QA and QC, it generally means that what are the methods that you are used to make sure your accuracy and precision is guaranteed or is satisfied. So for the accuracy and precision, let's recall that accuracy refers to the distance between the mean of our measurement and the reference value or the true value. And precision refers to the scatteredness of our sample. And in terms of instrumental analysis, we can measure these two values by different methods. So to evaluate accuracy, we can prepare fake samples by adding known amount of chemicals. And we can also add this known amount can also be 0, but we call this blank. And because this is a known amount of chemical which is prepared by us, so in this case, we call that the reference value. We do not call this as a true value. And to evaluate precision, we can use duplicated or triplicated measurement. And this is also a little bit abstract. We can see more detailed explanations, accuracy and fake samples. And to prepare fake samples, in general, we have two types of fake samples. The first one is matrix spike. So, which means a known amount of an analyte or representative components, they are added to a clean matrix in the laboratory. So the keyword is known amount. We know the concentration because we prepare that sample. And we also have the surrogate spike, which also we use a known amount of organic compounds, similar in behavior to the targets analytes, but they do not occur in the environment. And they are also added to the sample before processing. And again, this is also about the known amount. And we should also know that they usually do not occur in the environment. So in general, the matrix spike is analyzed as the methods of performance it is analyzed as a method performance assessed by measuring the effects of the interference caused by the specific sample matrix. And for the surrogate spike, it assesses sample matrix interference effects and laboratory performance. So basically, we want to make sure our sample is clean and our method, experimental method, is accurate, is correct, and there is no contamination during the experiment. And to quantify the accuracy, we can use the spike recovery, and it can be calculated after measurement, which is defined as, so the recovery equals to the concentration of the measurement divided by the concentration of the spike times 100%. And we can also see that the spike concentration, because we prepare the spike, so the spike concentration is a known amount, and the measurement concentration can be obtained. So we can calculate this value. And for a perfect measurement, we know that the measured concentration equals to the spike concentration. So the recovery rate should be 100%. And again, this is also a little bit abstract, and I will show an example later. And to measure precision or duplicate, and we can use duplicate. So basically, sometimes we can make the duplicate, or we can make the triplicates, and then we can evaluate the difference between the duplicates, or evaluate the standard deviation of the triplicate. So far, do you guys have any questions? No. And then we can have an example of the preparation of the sample. So I guess we can have a better understanding of those terms. So let's just suppose we want to measure the DDT concentration in soil of 3 different sites. Like we have site A, site B, and site C. So we have different sites here, A, B, and C. So first, we collect soil samples from these 3 different sites, and we can name them as A, B, C. So we take soil samples at different sites. And then soil samples were thoroughly mixed in a bucket so that DDT concentration in the soil sample was homogeneous. So when we get the samples from each site, we put them in the bucket, and then we just mix the soil in this bucket. Just make sure the DDT concentration is kind of homogeneous inside each bucket. And then we are preparing for a sample duplicate. Then we transfer the soil sample of each site into 3 columns for DDT extraction and for further analysis. So suppose like in this experiment, we need to extract the DDT concentration in the soil. And during this process, we need to use like the column like this. And then we can use the organic solvent to extract DDT from the soil sample. And in this case, we can prepare 3 columns for each sample so that we can have triplicate. And in this case, note that the concentration of DDT in each column is unknown. So they are all unknown values. And because DDT measurement needs sand to help with extraction, because like for some experiments, when we are doing the extraction, we need some stuff like chemicals to help with the extraction. And in this experiment, we need the sand, something like this. So clean sand was also added to each column. So we have the sand in each column. So basically we have the sample and the sand. And the true concentration of DDT in the sample A, B, C, they are unknown values. So basically we want to know their concentration and their unknown. So next, we are going to prepare the method blank. We want to make sure our method is correct or there is no contamination during the experiment. So we are preparing the method blank. Because the sand was introduced and mixed with the soil sample, we can prepare two method blank with sand only. We just want to make sure the sand is clean. So note it as sand blank SB to ensure that there was no any contamination during experiments. And in this case, except for this 9 sample array, we have this extra 2 columns with the sand only. And then the concentration of DDT of sand blank should be 0. So this concentration are supposed to be 0. If the final measurements of these 2 concentrations was not 0, we can say that there are some contaminations during the experiments or the sand is contaminated. Yes.
Is there a particular reason why you choose 2 instead of 3? Or the 0?
Yeah, that's a good question. Like to be ideal, it is 3, like it is good. But I choose 2 because I'm lazy. And also some people also only use 1. So it depends on the tradition of the experiments or based on the how to say experience. Yeah, but to be ideal, the 3 is the best one. Yes. And then we can prepare the matrix spike. So next, we prepare a set of matrix spike where we add sand and clean soil into the column. So we can have the matrix spike here where we have the clean soil and we have the sand. And the clean soil can be comes from other places that is not contaminated, or we can purchase it from some company that sells very clean soil. And then we add known amount of DDT. Note that this is a known amount of the DDT into the columns, and the known DDT concentration was CMS, like the matrix spike. So for now, we also have another extra 2 columns. And again, we can have extra 3 columns, but here I just show 2. And we know that this is a clean soil plus sand. And we have this CMS, C matrix spike. And we know that these 2 concentrations are also known value. So if the measured result of these 2 values does not equals to these 2, we can say there are some problems. And finally, we can prepare the surrogate spike. So for the surrogate spike in this case, or in our homework assignment, we use DDE carbon 13 was the surrogate. We choose this chemical because it's but similar, like it has a similar properties or similar chemical behaviors to the DDT. And it does not appear naturally. Or I would say because DDT is a pesticide, so originally it does not appear naturally. But when DDT was made, they do not have like CA13, like they do not have much of C13. So we use this chemical as a surrogate, and we know that the pesticide made with C13 does not naturally appear in the environment. And again, C13 is isotope, like where we have, and this 12 refers to we have 12 C13 atoms in this DDE molecule. And, and in this case, known amount of DDE C13 was added into every column. So we add this to every column for the surrogate. And the concentration of DDE C13 was CSS because this is surrogate spike. And by putting all of the columns together, there are 13 columns in total. And let's say we have 2 sand blank, which we only have the sands. And because we can consider it as a matrix spike and the concentration should be 0. And we also add the surrogate spike to the sand blank and the concentration is lower. And we also have another set which is clean matrix spike with the clean soil plus the sand. And in this case, we have the matrix spike concentration and we have surrogate spike concentration. And all of these concentrations are lower. And then we have 3 sets of our sample with triplicates. And the concentration of DDT is unknown, but we also add the surrogate to each of the sample and the concentration is known. So in this case, we have like 9 unknown values and we have 9 plus 4 plus 4, like 17 known values. So basically after the measurements, we are doing some statistics based on all of these known values. So far, do you guys have any questions? Yes.
So to make sure there's no interaction between the DDE and DDT, did you do a separate experiment or was it just all based off the literature?
Oh, this is a good question. So in this case, because we know DDT and DDE, they are very stable. And they do not have any interactions between these 2 chemicals. So we can put them together. Yes. So any more?
Literature.
Yes, based on literature, yes. So any more questions? Oh. Now, finally, when we have our extraction, we want to send this to the instruments like the GC, like gas chromatography. But before that, we need also prepare another set of blank, which is instrumental blank. So after extraction of DDT from all of the columns, we process the sample and finally transfer the sample into GCMS to determine the DDT concentration. But before that, 2 vials of instrumental blanks were added to the sequence. Because when we extract the DDT from the soil, we dissolve the DDT into hexane. Oh, so we can just see this one. The instrument blanks were filled with clean solvent. And in this case, the analytes like DDT, they was dissolved in hexane. So the instrumental blank is the pure hexane. And we put the pure hexane here. And then the measured concentration of the clean solvents or the instrumental blank, they should be 0. CIB should be 0. So if the CIB does not equals to 0, we can say there is something wrong with instrument or something wrong with the hexane. So there are all of our samples. And then for the QA and QC check, we can do these following steps. So first, we want to check if the measurements of DDT and DDE C13 or the surrogate of instrumental blanks is 0. So if the instrumental blank is not 0, we can say that there are some problems with the GCMS with the instrument. Then we want to check if the DDT measurements of sand blank and sand blank 1 and sand blank 2, if they equals to 0. And we know that they should be equal to 0. And if they do not equal to 0, there might be some contaminations in the sand or some contaminations during our experiment. These are general checks, and then we are going to check the accuracy. So for the accuracy, first, we compare the DDE C13 measurement of each column with CSS, which is a surrogate concentration. So basically, we compare the measured surrogate concentration with our known surrogate concentration. And so we can calculate the recovery of surrogate spike. Note that the surrogate spike equals to the C measurement divided by the spike concentration. And in this case, this is CSS, and then we times 100%. And then we compare DDE measurements of the matrix spike with the matrix spike concentration. So again, we compare the measured concentration with the concentration that we add. And this is the recovery of matrix spike. And then we can also check on the precision by checking the consistency between SB1 and SB2 and matrix spike 1 and matrix spike 2 of the measured value. And similarly, and finally, we just go to our measured sample. So this is the last step. We compare the consistency or the standard deviation of the measured concentration in A1, A2, A3, and for sample B and for sample 3. And after this whole process, as long as all of these stuff are good, we can say that the measurement of this result is reliable. And so for this one, do you guys have any questions? No? And there's one more thing I want to add. For the accuracy requirement, like we may have some like different measurements or different chemicals, they may have different standards. And in my experiment for DDT, we want it to be like 80% to 110%. So if the recovery is within this value, we can see the recovery is good. And in general, we usually have the recovery rate smaller than 1 because we have some loss. We will lose some of our samples during the process, but we usually do not obtain the chemicals during the process. So the recovery rate is usually smaller than 1. So any more questions? But that is the simplified version. In a real experiment, we have a little bit more complicated setups, which is calibration standard that we have already know, and we also have the standard check SC. So if a sample array is very long, then we need to add standard check in between the samples and the standard check. So this is a standard, like we have 6 standard calibration standards. And then we want to put some of the standards between the samples to make sure, because we also know the concentration in the standard. So we can also compare the measured value of our standard. And the standard check should be 1 or 2 more depending on the size of sample array. And the reason why we add the standard check is to something like that. If this array is very long, then we will take a very long time to do the measurement. For example, when we check this one, the recovery rate is good. But when we go to this one, the recovery rate is only 10%, which is bad. And in this case, we can see that we may say that the measurement before this array is supposed to be good, but the measurement after this array is bad. So we may use the measurement of this one, but we are not able to use the measurement of this one. And again, the exact order may vary case by case, and the number of sample of standard check also change case by case. So for this one, do you guys have any questions? Yes.
How do you choose the range of concentration for the calibration?
Yes. So for this range, we usually choose like, because we have our sample concentration, we have like a rough range. So basically we can put the standard check with the similar range of our sample. Is any more questions? Yes.
Sorry, okay, so we're just about that. So you put the standards in between different like parts of the array to like check the R?
Yes, to check the recovery, because for the standard, it has the known concentration, and we can also have its measured concentration. So we can also calculate the recovery of this is a measured value, and this is a known value. So we can also check the recovery of the standard. Yes, but in this class, we are not going to ask questions about the recovery of the standard. But I want you guys to know, like we have these techniques to make sure we have good QA and QC. And here I also want to show that we can see when we are making measurements of only 3 samples, we have to prepare a large amount of extra samples. In other words, doing the lab experiments is very tedious. So it is very hard. Okay, and here is an example of the result. This is very small, so let's make it a little bit larger. So this is the result of my experiment. We can see this shows the sample array, and we can see this is a standard 1, standard 2. So first we have different standards. And then we have this hexene, which is the instrumental blank. And then we have the concentration in earthworm. So in this case, it is not the soil, it is the earthworm. And we have different measurements, like we can say we have triplicate. And we have S and B. B refers to the big worm, and S refers to the small worm. I just separate the big worm and small worm. And then we have this matrix spike. But in this experiment, we only have 1 matrix spike because preparing this sample takes a long time. And then we have another sand blank. And then we have the hexane here. And finally, we have the 2 sets of standard check at the end. So this is the array of my experiment. And let's see, we have this PCNB response. So basically, this refers to the how to say, the absolute value of the response of the instruments of the GCMS. But in this class, we do not care about this. But in general, we want to make sure the response of the instruments are consistent. So they should be like the values should be very similar. And we can say this is not quite good, but it's okay.
Is it the area?
Excuse me?
Is that the area of the curve?
Yeah, I think yes, yes, yes. So this is the area of the internal standard, but in this class we do not have to worry about this one. And then this is a concentration of different chemicals. Like in this case, we have 6 chemicals, like OPDDE, PPDDE, and blah blah blah. So they are DDT or DDE of different spatial structures. And we also have the Delgim. And in the last column, we have this PPDDE C13. So this is our surrogate. The surrogate concentration is also reported. So, and here we have the recoveries. So this is a recovery of our standard. And in this class, we do not care about that. But here we can just see, because we know the concentration of the standard. So let's just look at this first. And at the bottom, we have the standard. Like we have different standards and we have different concentrations. When we are making standards, we want to make sure the standard values are like the integer or looks good. But when we are exactly preparing the standard, it may be like different from a perfect value. So we just record this value. So like we have the standard of different concentrations. And this is a standard of the surrogate, like C13 of the DDE. And we also like this are the concentrations of the internals of the surrogate. And on the right side, here shows the matrix spike or the surrogate spike, which are the known concentration that we added to the sample. So this is a matrix spike of DDE and for the different chemicals. And this is the surrogate spike concentration of this DDE C13. So when we go back to this one, this is just the recovery of our calibration curve. And we can see some of them are pretty bad, like this one, but that's fine. Okay, so in this class, so first we want to evaluate if the sand blank, if the hexane, which is the instrumental blank, if this equals to 0. And we can see the instrumental blank, which is hexane, equals to 0. So which means it is good. And then we look at the sand blank. So the sand blanks are here. We can see the sand blank are 0 for all of the samples, but the sand blank is not 0 for the surrogate spike. And we also have another sand blank. We can see the measured concentration equals to 0, except for the surrogate spike. So the sand blank is good. And then we can compare the matrix spike. So the matrix spike concentrations are here. And we know that these concentrations are known because we add them. So we can compare this concentration with here, because these are also the matrix spike. We can calculate the recovery. And finally, we can compare the surrogate spike. The surrogate concentration is known here. And this column are also the surrogate concentration. So we can calculate the recovery rate of each of this one. And finally, we can compare because like we have 3 groups. So we can calculate the standard deviation of the 3 values and to see if these values are consistent. So this is about this table. So do you guys have any questions about this one? No? Okay, so when you guys are doing the homework, you can just revisit this page. And this is the end of the lecture. Here, I just want to say for quiz 7 and assignment 5, they are due on this Thursday. And we also have an extra lecture, like the professor highly recommended. I'm not sure if you guys receive the email, something like this. So this guy will be talking about like career journey, strategy, pandemic, and hybrid infrastructures. And you can register at this website. And I also post the information on Canvas, like in the discussion boards, we will have this page. I just copy and paste the information here. So if you're interested, you can go to here. And here I just want to say, because this is not part of this class, and we also remember that for the Excel sheets, I have the column that is for the extra credits with 2.5% of the total. So if you guys are interested, you can attend this lecture. This can be virtual, although it is like 1 hour lecture from 1 to 2. You guys will not have the lab, but the time may be very tight. So you may just attend it for half an hour or 20 minutes. That is fine. But I want you guys to post your comments or your thoughts or any notes of this lecture on the discussion. And then I know that you attend this lecture, and then finally I will add like extra 25% of the total grade when I'm calculating the final grade. So that's all for it today.